Okay, welcome to the section lecture number 2. Still we have an introduction. So this introduction means that we are not talking about, it does not necessarily mean that we are talking about introduction. So introduction is actually the title of our chapter number 2. In this lecture 2, we will talk about the types of logic you can consider here. So before starting our today's lecture, so let me just really briefly review our previous lecture, lecture 1. So that was, our previous lecture was the very first one, lecture 1. And at the time we have thought about the MOS transistor, so metal, oxide, semiconductor, transistor. Here MOS means the particle structure, so metal, oxide, and semiconductor. So here we have a certain contact called as gate, and this silicon part, substrate part, is connected to the body contact or substrate contact. So the goal of our MOS structure is changing the gate voltage, so to control the number of electrons or holes which is found at the beneath of this oxide layer. So usually for MOSFET, if we apply higher and higher gate voltage, then we will have more and more electrons. So that gives us some capability to turn on our device or turn off our device. So maybe you remember that. So I have told you about two different mechanisms to control or change the negative charges collected in this substrate. So one was electron, collecting electrons, and that is typically called as inversion behavior. And another one was depletion charge. Combining both of them, when your gate voltage is not that high, then this depletion mechanism is the dominant mechanism to supply the negative charges in the substrate. And when your gate voltage is high enough, then now inversion mechanism becomes the dominant one to control or to supply negative charges in the substrate. That was explained. So the role of gate and body is just to control the number of charge carriers. And please come in. Yeah. And the current itself is not conducting through this gate and substrate. Instead, we introduce another two contacts, so-called source and drain, and apply the voltage difference between these two. So VDS is applied, and by using a non-zero VDS value, we try to make a certain current conduction between source and drain. That was explained in our previous lecture. So in the case of MOSFET, where electrons are charge carriers, then yes, when gate source voltage is lower than certain value called threshold voltage, typically positive value, and just a portion of our VDD. Then when gate voltage is lower than that, then no electron can be found in the channel region. On the other hand, when our gate voltage exceeds the threshold voltage, then electron density now increase linearly with VGS minus VTH. Sometimes that is called as gate overdrive voltage. So this quantity becomes the driving factors for um, our how can you say, our the mechanism to collect excessive electron under the channel. And these are related with the P and MOSFET. However, we have a dual device type, so-called P MOSFET. So here P means positive, and that means that we have now holes as charge carriers. So in this case, now our VGS should be lower in order to collect more holes. So, and if VGS is higher and higher, then now we have less and less holes. So they have MOSFET and PMOSFET behave exactly the opposite way in its voltage polarity. So that the existence of this PMOSFET quite unique for our silicon CMOS technology. As I told you before, for other technologies, so seemingly quite promising. However, it is very difficult to find this kind of whole dominant um, whole dominant device. That is a pity for many other technologies. So that was a really short summary or review of our previous lecture. Do you have any question about our previous lecture? So no, no. So it is really always recommended or encouraged to have any question to me. So please give me any question, then I will be more than happy to answer your questions. So okay, if you don't have any question, then today we will talk about the section 1.4 devoted to the description about CMOS logic. We have many topics to be covered, but I will try to as much as I can. So, this is just showing the simplest CMOS logic circuit, CMOS inverter. Here, inverter means that actually the thing which can perform logical not operation. So you know that when this is the input and this is your output, when input is 0, logical 0, so logical 0 means that the voltage close to what? Close to 0 volt. And logical 1 is, yes, the voltage close to, in this case, VDD. Who decided VDD? That is given by the system. So when you first try to design something, then your VDD is the very first one to be determined. So now you have this voltage close to 0 and close to VDD. And let's think about this one. For example, happen to be this is 0.7 volt. Then I want to ask this simple question. 0.1 volt. Is this logical 0 or logical 1 or 0.6? Is this logical 0 or logical 1? Maybe you feel that this would be maybe logical 0 and this would be logical 1. So you are right. But why? It is because this system, our digital system, have some margins and some tolerance. Although it is not exactly 0, but it has some tolerance to accept certain values close to 0 or certain values close to VDD. So let's think about a certain system which has really narrow tolerance and margin. So say that to me, this is a VDD and this is a 0, and to me only this voltage range is regarded as logical 0, and to me it is also regarded as logical 1. So, sorry, this number 1 is. This is quite a narrow system. So do you like it? So it is not, because then your system becomes really weak to certain noise. If your ground value is slightly degraded or your VDD value is slightly degraded, then your logic system sometimes say that, oh, now it becomes just gray in the gray region, whether I cannot understand whether that is 0 or 1. That is not a good case. Or, however, if we have a more tolerant system like this and that, what happens? In this case, wow, although you have a certain deviation from the perfect values of 0 or VDD, but that would be, your system would be robust against that kind of perturbation in your signal level. Anyway, in our notation or in our terminology, so the voltage really close to 0 or voltage really close to VDD are called as strong signals. And the, the signal which are slightly moved from that strong signal, for example, this value or that value, those values are treated as still logical 0 or logical 1, but that is not perfectly matched to VDD or V0. So in this case, we say that these are weak signals. So let's say that here we have a certain signal, the system, and here we have input and output. If you have a strong signal, what you want to have is strong signal. That is not that difficult. Then how about this one? You have a weak signal and you have also weak signal. Well, that is quite reasonable. However, you don't like it. Although you have a weak signal here, actually what you wanted to have is your weak signal was regarded as logical 0 or logical 1, then your signal should be once again strong signal. So let me just come back to our inverter example. In our inverter example, you have this truth table. Your logical 0 is converted to logical 1, and your logical 1 is converted to logical 0. Then let's think about this one. One case. You have, for example, exactly 0.0 volt. Then it will generate 0.7 volt. Great. However, that's not that difficult. But point is, once you have 0.1 volt, let's think about a system which generated just 0.6 volt as your output. Since my input was weak, so output is also weak, I have to accept this condition. However, this is not. The desirable condition is, although you have just 0.1 volt, which is quite weak, but now once after this inverter operation, now your signal is restored and it becomes once again weak. Oh, sorry, not weak. Once again become strong signal. So that is desirable property. So are you with me? So always in our input port, we can have such a kind of thing like called noise, which is not undesirable signal. However, this is unavoidable. So when we have such kind of thing, our system should be robust enough to generate strong signal. Okay, so anyway, now this is inverted truth table. Then how can we achieve this kind of operation using our transistors, both of N MOSFET and P MOSFET? That is explained in this graph. Okay, so let me just go to here. Here we have N MOSFET and here we have a P MOSFET, and please recall that this is a switch and this is another switch which are reacting to voltage 1 and voltage 0. Means that when we have gate voltage close to the logical 1, then this switch is turned on. So you can easily understand this behavior. So think about this one. When we have a logical value 0, A equal to 0, now we are looking at this one, then our N MOSFET is turned off. So it is not conducting any longer. And in the case of this 0, on the other hand, our P MOSFET just switched on, and now we have a strong connection between our drain, this is the source of our P MOSFET, and drain. They are well connected. So from the viewpoint of your output node Y, what happens? Now you have a strong connection to VDD, and when we talk about the connection to the ground here, and unfortunately they are disconnected. So then what will be the value of your voltage Y? Your voltage Y will be just VDD. So V sub Y would be VDD, and this case is regarded as your logical value for Y is logical 1. That is not that difficult. And when you go to the second part, so when we have a logical value 1, then the situation becomes the opposite. In this case, our N MOSFET is now turned on, so our logical node Y is connected to the ground and disconnected to the VDD. So as you can see, this one has very simple, this inverter has very simple rule. Either only one of N MOSFET and P MOSFET is turned on and the other one is turned off, because both of them are controlled by the same signal. And since N MOSFET and P MOSFET has different operational rule for gate voltage, so either one of them is turned on. Then now voltage is so-called pulled up or pulled down. So this part is called as pull up circuitry, and this lower part is pull down. It is because we are usually drawing our circuit schematic for higher voltage part and lower voltage part, higher for up and lower voltage for down. Okay, so it is not that difficult. And let's go to a slightly more complicated system like a two-input NAND. Two-input NAND is actually not of our AND. So you know AND, in the case of AND, now in this case, no. Okay, so your AND case A and B, Y, 0, 0, 0, 1, 1, 0, 1, 1. In this case, this becomes 0 and this becomes 1, and this becomes 0. Since it is the AND, this is 0 and this becomes 1. And since our output is not just AND but not or This is and NAND is inverted AND, so we will have 1, 1, 1, 0. So this truth table is correct one. Then how can we, once again, achieve this goal? So please try to understand this way. In order to achieve logical value 0, we have to provide to the path the ground. It means that when A equal to 1, B equal to 1, only for this case, we have to provide path to the ground. So for example, here we have two different transistors, one transistor and another transistor, and they are connected in a serial way. In this case, in order to provide to the ground, here we have ground. The case we can provide connected line is this switch is turned on, also this transistor is turned on. However, think about the opposite case like this one. Here we have B signal and A signal, and they are both of them parallelly connected to Y, and they are connected to ground and ground. In this case, if we have these parallelly connected transistors, then when any of A or B is 1, is 1 or 1, or both of them are 1, in this case we can provide the path to the ground. So if we have such kind of pull down device, then we can write down in this way A, B, and Y. If we have such kind of thing, then when it has 0, 1, 1, 0, 1, 1, for these three cases, any of A or B is 1, then now we can provide the path to the ground. So how about this truth table? Is it corresponding to our truth table for a NAND gate? So certainly not. So this cannot be a solution. On the other hand, if we come back to our NAND implementation shown here, figure 1.12a, then we can find a serially connected line, and these serially connected two transistors provide the path, connected path, only when this is turned on and this is turned on. Only case for A equal to 1, for B equal to 1, now we have path to the ground. So simply speaking, for this case, now we can have this 1, 1 equal to 0 case. So are you all with me? We are now talking about the pull down part of our NAND gate. Then, wow, we have achieved at least the pull down circuitry. Then how about the pull up circuitry? For all other three cases, here and here and here, now this root is disenabled. So we have no electrical connection to the ground. On the other hand, we must provide the path toward now VDD. So how can we provide the path toward VDD and path toward VDD? So here you can see that our PMOSFET and PMOSFET are now parallelly connected. So please note that they are in the pull down part, they are serially connected, and in this case we have parallelly connected PMOSFET. Then when you just consider their operation, then you can find the case. For example, 0, 0. 0, 0 case means that these two P MOSFET transistors are turned on. Good. So we have both lines, both root toward VDD. And 0 and 1 case, in this case only A transistor is turned on and this guy is turned off. But it's okay because they are parallelly connected and at least one of them is connected to the VDD, then its value can be VDD. Okay, so are you with me? So this is quite simple, but now think about this one. Inverter, NAND, or NOR, they are quite easy. But is there any rule for us to make this pull down and pull up circuitries automatically? So that is shown here. Oh, sorry. We have to discuss about this later one. So we must first consider this third slide. So now let's generalize our concept. So up to now we have thought about inverter and NAND gate, and they introduced two different circuitries. One was pull down and one was pull up. So when we have a certain input signal, only one of them, pull down or pull up, is activated. So we have either the path toward ground or path toward VDD. That is our previous examples, inverter or NAND gate. So in this case, think about these two cases, pull down and pull up. They are either turned on and turned off. So our operational range is like this, here and here. In this case, we have when pull down is off and pull up is on, yes, then VDD will be your output voltage. And when pull down is on the other hand, pull up is off, then you will have just 0 volt as your output voltage. So you don't worry about this case or this case. But this is not automatically obtained. So let me just give you a counterexample. Think about this one. Now you have here we have a PMOSFET and PMOSFET. And let's say that here we have a ground and here we have a VDD. And you have a AB, AB. Yes, and I will call it as this part as what? This part as pull up. Yes, and I will call it as pull down. So please try to think about its operation. So when you have 0, 0 condition, 0, 0, 0, 0 condition, so what happened? Now this pull down is completely shut off and our pull up is now connected. Good. Now the output will be logical 1. And how about 1, 1? So instead of that, 1, 1, 1, 1, 1, 1. In this case, on the other hand, pull down is turned on, so your logical value would be just 0. electrical shortage here. But anyway, we will have the output 0. It's okay, but think about this case. 1 0 1 0. Then what happens? Your pull down circuitry is now turned off. Although this guy is switched on, but serially connected this guy is turned off. Also, this one becomes active, but this one becomes inactive. So none of them is actually switched on. So in this case, what happens? So in this case, we have the state where our output is not connected to any of 0 and VDD. Then what happens? So logically, it is difficult. It cannot be easily determined whether that is 0 or 1. That is actually, at least in this case, undesirable case. Okay. So then, why we have such kind of thing? The reason is our pull down and pull up devices does not obey a certain rule. So let me just go to the rule between pull down and pull up to make such kind of a complementary CMOS gate. Simply speaking, we have to obey the conduction complement rule between pull up and pull down device. When we have one given pull up device or one given pull down device, our pull up device or pull up circuitry should be constructed following the rule of conduction complement. Means that like this: if you have serially two transistors and A and B, then in order to build complement CMOS gate, then your pull up circuitry should be written like this way. Your A was serially connected, and these serially connected transistors should be placed in a parallel way, A and B. That is simple rule to build. So in this case, when your transistor when your pull down circuitry fail to provide the path toward the ground, then your pull up device constructed in following conduction complement rule always provide successful path toward VDD. Then let's come back to our previous examples. Yes. NAND gate, pull down was serially connected. Then pull up are parallelly connected. Then let's think about another example. Another example, the simplest one would be like this. If you have, for example, parallelly connected pull down, then please try to build your pull up circuitry following the conduction complement rule. So what should be the pull up circuitry? Since they are parallelly connected in this pull down, then pull up case we have to have serially connected transistors for our two input signals. Then it will give you the logical operation of NOR. Okay, so that is shown here. This is NOR. Here A and B. So you can easily check the truth table A and B. The best way is, in my opinion, 1, 1, 0, 1, 1. Concentrate on your pull down circuitry. Then try to, when you have the path, in this case, you can provide path toward the ground when either any of A and B is turned on. So here you will have 0, 0, and 0 for all three cases. When, sorry about that. So I was mistaken. Here, sorry about that. Sorry about that. Here we have this case. When any of our transistor is turned on, then we have the path toward ground, and we have to talk about only the case of this 0, 0 case, and this 0, 0 case, our A and B transistor, this P MOSFETs are turned on and turned on, so it can provide a path toward VDD, so it becomes a logical 1. Wow, good. So let's go to the example 1.1 of our textbook. Then sketch a 3-input CMOS NOR gate. Then how can you do that? If we have A, B, and C as our input signals, then the pull down would be A, B, C in this case, A, B, C, because this is NOR and this is inverted OR, and this OR can be achieved by these parallel transistors. And the upper part would be, once again, serially, also serially connected 3 P MOSFETs that will give us the 3 input NOR gate. Okay, so are you all with me? So I think that is not that difficult for you to understand this simple rule. Then now let's go to the other examples. So up to now we have thought about the NOT gate, inverter, and NAND 2, NOR 2, and we just considered NOR 3. These numbers just represents the number of input signals. So NOR 3 means that 3 input nodes. And now we are talking about the other functions like this. So first take AND of A and B, and take the AND of A, C and D, and take OR between their result, and take the inversion. This is, say that this is our whole Y function. Then it is typically called as AND or invert. So because first we take AND and we take OR, after that we invert the final result. Okay, so that is shown here. Then if we have to build this one from just the brute force way, then what we have to do is A, B, and we must introduce AND gate, and C and D, and we must introduce another AND gate. After that, they are combined, and we have to have another OR gate, and finally we have inverter here. That is the one we have to have. This is Y function. But you know that if we build in this way, then how many transistors are required? If we just separately, let's try to separately implement AND, OR, and inverter. Inverter, we have 2 transistors. And or cannot be directly made, and we can think about nor followed by inverter. Of course, this inverter and this inverter can be cancelled out each other, but for why? Don't think about that. Then NOR gate, how many transistors we have to have? 4. So are you with me? Previously, when we have a look at this NOR, we have to have 1, 2, 3, 4. 4 transistors. And inverter, we have 2. Once again, in this AND gate, we have to have 4 transistors for NOR and plus 2 transistors for an inverter. So 6, 6, 6, 2. So we have 20 transistors required to implement this capability. Of course, I wanted to say that in this case, we don't have to actually have these two of inverters once again, because here we have one inverter and another inverter, so they can be omitted, but still we have many transistors to achieve this complex logic function. However, we have another way to achieve it. So think about this one. So this function y is finally inverting. Here we have finally inverting function. So it means that, simply speaking, our pull down circuitry is activated when AB plus CD equal to 1. When we have this condition, our pull down circuitry is on. This is quite simple. Then it means that once again, this one is once again means that AB equal to 1 or CD equal to 1, our pull down circuitry is turned on. Then how can you achieve AB equal to 1 condition? AB equal to 1 condition can be easily obtained by serially connected A and B. So it means that when you have this kind of serially connected A and B, then only when A equal to 1 and B equal to 1, we will have the turned on pull down circuitry. And we have OR CD equal to 1. So OR can be regarded as parallel circuitry. So now we have CD. Wow, this is the implementation of our pull down circuitry. So please once again think about one. How can we achieve the connected path toward ground? The possibility is AB equal to 1 or CD equal to 1. If we have such kind of thing, the Y will be 0. Otherwise, by following the conduction complement, we will have logical value 1. So that's the reason why we have a final inversion in this case. So now, once we have this kind of a pull down circuitry, then it is easy to make this pull up circuitry, because A and B are in parallel. Now they are serial, and they should be now in parallel. C and D are in serial. Now in the pull up circuitry, they should be also parallel, and they are parallel, they should be now in serial. So this is not that difficult to make this compound logic gate. So now think about this one. when you have lower transistors, what happens? If you have lower transistors, then first of all, you have a smaller area consumed by your transistors. That's good. Also, uh, another beauty is since we have a lower number of transistors, its power consumption can be reduced. Oh, that is also good. And another one is, since we have a smaller number of transistors, the time to charge up and charge or discharge these these internal capacitors can be reduced. So always it is good to have this simple implementation for our complex logical functions. Of course, now that can be done by our computer programs. When we have a given logical function, then it can suggest us to use this kind of already built compound gates to reduce the burden for our design. Okay, so now we understand we can now build basic universal functions like NAND or NOR and simplified one like inverter. And also we can build any given logical function, inverting logic functions, so by using certain simple rule. For example, example 1.2 asks us to design this function. You know that this is once again inverting one. So our goal is the condition where a plus b plus c multiplied by d equal to 1 as a pull down circuitry. So now you know that since we have here multiplication d, so d should be multiplied, and a, b, c are OR functions, so they can be written as parallel way. Yes, yes, and another yes here, a, b, c. If we have this one, then in order to active, in order to activate this pull down circuitry, oh sorry about that, a, b, c, then we have to provide d equal to 1 and any of a, b, c equal to 1. So this is pull down circuitry. Once after your pull down circuitry is built, then building the pull up circuitry is quite easy because this guy and this guy are serial in this case. Now in our consideration pull up, we have to have a parallel connection between this guy and this guy, and internally ABC or in parallel in pull down, and now ABC should be in serial in pull up circuitry. So you know that is not that difficult to understand. So now let's go to a little bit different concepts. Up to now, we have talked about a family of logic family called what? Called this one, complementary CMOS gate. So this is complementary CMOS gate has pull down and pull up circuitry, and it is built following the conduction complementary rule. Then everything becomes quite easy and straightforward. Mhm. But please note that we are always hungry for efficient implementation of our logical function. That's the reason why we are now talking about different ones, like test transistors. Test transistors, here, transistors can be used as switches. You know, up to now we have always talked about this one. Here we have a signal A, and when signal A equal to 1, then this source and drain are connected. So that was the rule. So now think about once again source and drain and gate. When it means that the gate becomes 1 and source and drain are connected. So you are now looking at this one. You all agree with this one. And in the case of your PMOS pad, how about that? In order to turn on your transistor, PMOS transistor, you have to provide logical value 0 because your PMOS pad is turned on when the gate bias voltage is low. Then you have this connected one. So up to now, are you all with me? Your transistor, MOSFET transistor is turned on when your gate voltage is VDD. And I'm saying that your PMOSFET, when your gate voltage is 0 volt, then your transistor is turned on. This is the thing I have explained up to now. But please note that here, even in this case, now think about this one, these two cases. Now, your gate voltage is always 1 for your MOSFET and 0 for your PMOSFET. Now you think that, okay, transistor is now turned on and source and drains are connected. You are right. You are right, quite right. So let's come back to our drawing here. Our MOSFET is drawn here. Now we have gate voltage equal to VDD. Then now think about this one. Here we have ground, for example. Then what will be the value of your drain voltage? Since this, yes, you're right. Thank you for your answer. And this is ground. Good. This is perfect, and we have used this rule up to now. But now I wanted to ask you one simple question. Unfortunately, this is connected to VDD. Then what happens? Please note that the value, the driving force, the motivation to turn on our transistor was not simply VG. Do you remember? Actually, it was the difference between gate voltage to source voltage. So then if we have this one, and let's say that this is drain, source, then what is the voltage difference these two terminals? 0. So then is it turned on? Actually not. So our discussion up to now, when gate voltage equal to VDD and transistor is turned on, is implicitly assuming that one of our source or drain, actually source, is connected to the low voltage value. So that's the reason why always, although we have to consider rigorously VGS minus VG minus Vs, since Vs equal to 0 volt, then always Vg can be used as a representative of VGS. However, if we have high source value, then this transistor is no longer turned on. So let me just come back to our textbook figure. So now this one is shown in here. When we have 0, this is input and fixed, and source is 0 and gate is 1, then you know that the difference between this and that is just 1. It means that VDD. So now it becomes really 0 because transistor is turned on, so this is really connected. However, in this case, 1 and 1, what happens? So between this and that is difference between this and that is just 0. So you know that although gate is 1, but it cannot be perfectly copied into this one. So in reality, I will explain later in our lecture progress. Then in this case, the output would be degraded, or in our terminology, weak one. So how weak is it? Actually, this one is corresponding to VDD minus VTH. So this becomes the output of our single transistor. So same thing can happen to our PMOSFET. Although we believe that PMOSFET is turned on when the gate voltage is logical 0. However, it is true when we have an input of 1. In this case, we can pass this 1 to the output. However, in the case of input 0, then the output is not perfectly 0, and that is degraded. So that should be understood. Okay. So therefore, both of MOSFET and PMOSFET are not perfect to send a signal, input signal, to the output. So we have made this kind of transmission gate. Both of MOSFET, this is upper part MOSFET, and PMOSFETs are connected to each other. Then in this case, we can have strong pass of a signal. So think about this one. Well, let's say that this is 1, G equal to 1, and PMOSFET is biased with inverse of G. So here we have 0. Now we understand when A equal to 0, then this upper part, MOSFET, can transfer strong 0. That was good. However, now let's think about a case where our input variable A is happen to be 1. Then what happens? This input signal 1 cannot be passed strong enough by our transistor and MOSFET, because in this case it has just weak capability to pass our signal. So let me just come back to our previous slide. Here for MOSFET, when we have G equal 1 and input is 1, then it has just degraded capability to send or pass the input signal to the output signal. However, in the case of our PMOSFET, when PMOSFET is biased to the logical 0 in its gate voltage, then it can pass the input signal 1 in a strong enough sense. Now, this can be possible. So let me just say that. Okay, let me just draw once again. Input signal 1 is coming, and it has 2 paths and 2 paths. The upper path is called as MOS path, and lower path is PMOS path. In this case, when G equal to 1 and G bar equal to 0, then this MOS path becomes quite a weak path. I cannot pass you completely, sorry about that. But now P path says that, okay, I can pass you strongly enough. So you have a strong 1. That is the situation. And in the case of signal 0 and signal 0 is comes in, then right now P MOSFET pass say that, oh, now I cannot provide enough capability to pass you the output. Following my path, the signal becomes weak. But now this MOSFET path can provide a strong path toward the logical value 0. That is obtained by this one. Up to now, I have discussed about G equal to 1 and G bar equal to 0 case. However, also when we consider G equal to 0 and G bar equal to 1, same can happen. You can do it quite well when you have G equal to 0 and G bar equal to 1. Please think about 0 case and 1 case for your input variables. You will find that at least one of them, NMOS path or PMOS path, becomes strong enough to pass this one. Okay, so are you all with me? But here, that looks quite good. That looks quite good. But here I have one. So let me discuss about the weakness of this one. You love it, I love it, but here we have one thing to be more considered in this circuit. Say that now instead of this 0 and 1, let me just explicitly write down its voltage value. Now let's say that this is a VDD and this is 0 volt. Good. And now you have 0 volt and this one becomes perfectly 0 volt. That was the thing I have explained up to now, and you know that although in this case PMOS path is not strong enough, but NMOS part is strong. So therefore we have 0 to 0 transition. Good. But my question is, how about 0.1 volt? Now I introduce a slightly weak signal to this transmission gate and try to understand what will happen to our output terminal. Well, if this is a pass transistor, is it just copied into 0.1 volt? Or since this is just a logical one, so now it becomes just 0 volt. That is my question. So now think about this one. When we have 0.1 volt as a source of our transistor, NMOS transistor, and gate is VDD, then what happens? Since we have a sufficiently large voltage difference between gate and drain, yes, so now our MOSFET is still strong enough. And when they are strong enough, this source voltage is just copied into our drain voltage. So are you with me? That's the reason why our output becomes just 0.1 volt, not in 0 volt. Okay? Please understand this case. Let's say that if we have 0 volt, then what happens? If we have 0 volt, then now once again, since this 0.1 volt is fixed, then now this B terminal is working as a source, and now this is once again the voltage is increased until when our case becomes 0.1. So please note that in this case, when you have weak signal, then output becomes also weak signal. Please note that when you have your inverter, what happened? 0.1 volt. What was the result? Or if you have a change of two inverters, so now you have twice inversion, so you have the same value. What happens? 0.1 volt. After that, it becomes 0.7 volt because this one weak signal is restored to a strong signal. After that, this one gives you perfectly restored signal. Although you have weak signal, after twice of your inversion function, then you have strong signal. But in this case, it's not. Although it is fast, but it has still weak signal. So it means that transmission gate is not very robust against noise signal. So then that is thing. But so mhm. so so now we are talking about class of cases called tri-state. Tri means that three. Usually when you consider logical function, we have just 0 and 1. And 0 and 1, of course 0 is a case where voltage is close to 0 volt. And 1 is the voltage close to VDD case. However, in this case, we introduce another state called floating. Floating means that why we have zero signal, why we have VDD signal. It is because, in our circuit, we have a lays. Lays means that long line of metallic line. And that is connected to the ground. And that is connected to VDD. And when our signal is either 0 or 1, it means that our circuitry is connected to the VDD or our circuitry is connected to the ground in electrical sense. So that's the reason why we have logical 1 and logical 0. However, if we introduce intentionally a case where our circuitry is not connected to the VDD, not connected to 0, ground, then who knows what is the voltage of this one. Of course, in order to determine the voltage of this output node, we have to consider the transient simulation. So transient effect is important because previous value is important and we have to consider all kinds of capacitive components. But at least in this case, this one, it is kind of undetermined signal. We cannot certainly say that that is attached to 1 or that is attached to 0. That is the thing. So now think about one truth table of a tri-state buffer. So, tri-state buffer here. A tri-state buffer is just a buffer. A is copied into Y. So Y equal to A. So this is buffer. A is copied into Y. This is buffer. Good. Yes, that is quite good. But why we have tri-state buffer if we have only this one? This is just buffer. However, we introduce another controlling signal called as enable. This buffer-like behavior is enabled only when we have a logical function 1, 1. And when we have a logical value of enable equal to 0, so we will call it as a disenabled state. When this tri-state buffer is disenabled, although we have a logical value 0 here, it is not copied into Y. Oh, although input is Y, input is 0, but what is value of Y? I have no idea. That is the case. Oh, so it means that this enable signal is like a gatekeeper. Oh, here we have a gate, small gate, and this is controlled by enable signal. Then signal A comes in. Wow, I will try. I will pass this gate, but when this enable signal does not allow, then this Y is not affected by this A input signal. Only when, okay, pass enable signal becomes 1, then this A signal can be copied into our Y signal. So then now let's come back to our transmission gate. So now previously we have talked about this case when v g equal to 1 and g equal to 0. G by is always the inverse of g, so 1 0 or 0 1. Two configurations are available. In the case of our g equal to 1 case, then yes, our transistor, NMOS transistor is turned on and PMOS transistor is also turned on. So they can pass. But when we have 0 and 1 case, my question is our MOSFET is turned on? No. And our PMOSFET is turned on? Also, no. So, simply speaking, this A and B terminal are electrically disconnected. That is achieved by this configuration. So now when you come back to this slide, then we can find that actually this is it. Transmission gate can be used as tri-state buffer when we have G equal to 1, then A is copied to the B. But when we have G equal to 0, then A and B are disconnected and B is left as undecided, undetermined over floating. That is the thing we can have. Okay, I think that time is up, and in the next lecture we will really briefly talk about remaining contents in our presentation material, and we will move to the fabrication process of our CMOS circuit. So that will take one more lecture hours. So do you have any question on today's lecture? Or any question is really welcome. No? Okay, then let's wrap up today's lecture and see you next Tuesday.